Okay, welcome back. Last time we finished up with buffering, and so we're going to be moving onward. Next, quality of service metrics. Okay, so metrics is just a fancy word for measurements, right? Basically, some numbers associated with something. So how do you measure quality of service? Well, here we go. So remember, number one, quality of service inherently means different things to different users of different applications, right? So it's not one single variable. You can't just say this application has a 9 on quality of service and this other one has an 8 and expect that to be meaningful, okay? It's more correct to present quality of service as a set of metrics that include things like latency, jitter, how many packets you're pushing through the network per unit time, stuff like that, okay? And then the user or the network administrator can decide, does that cluster of performance metrics, does that indicate that things are going well or not? Okay, the other, alternatively, quality of service can be considered in terms of essentially how happy users are, right? So number one there, how well performance meets a desired operating standard. You know, if you're supposed to be showing video at 24 frames per second and such resolution, and you're meeting that, it doesn't really matter what else is going on in the network, right? You're meeting your performance target. Likewise, it could be just in terms of user satisfaction levels. For example, do users feel like the web pages are loading quickly enough? Or do they feel like the video is playing smoothly, right? Regardless of what's going on behind the scenes with those numbers, if the users are happy, they're happy, okay? All right, now, a little more stuff. More about quality of service measurement. So, you may have heard the term peak to average ratio. That's the idea fundamentally. Sometimes your network is really, really busy. Sometimes it's not so busy. So, what often happens in life is your network will experience transient bursts of activity, right? So, let's say this is a time graph, and this is 12 a.m., and this over here is 11:59 p.m., right? So we got one full day cycle. Maybe your network activity, it's really quiet during the day. It's a little spike in the morning around 8, little dip at lunch, early afternoon spike, maybe a big late evening spike, something like that, okay? And this is not too far off from a lot of applications that are designed for ordinary users, right? They tend to be busy in the evening when users are off work. They may experience some other kind of surges in traffic. For example, way back in the day with America Online, when we had, again, our shitty dial-up connections and we were glad to have them, AOL never had enough capacity to meet demand back in the 90s. So what would happen, anytime you wanted to log on between midnight and 6 p.m. or 9 p.m. and 6 p.m., it was fine. They had plenty of capacity to handle that sort of average level of traffic. But the number of people that wanted to get on between 6 and 9 was some kind of big burst like that. So essentially what happened, right, if you wanted to get online in the quiet hours, it was no problem. If you wanted to get online during the busy hours, basically you just had to sit there and click redial for anywhere from 20, 30 minutes until late 90s they started sorting out that capacity problem. Okay? So that's what we mean by this sort of peak to average trouble. The question is, depending on how long this peak is and how many users it affects, and how often it happens, is it every day or is it once a year? How much basically capacity safety margin do you have there? Do you have your capacity level up here so you guarantee that you can serve everybody? But then what happens? You have a lot of idle capacity, right? 19 hours out of the day. So you're paying a lot extra. On the other hand, if you're not making everybody happy, depending on how many alternatives they have, they might go somewhere else. And the question is always, what the trade-off is. How valuable are the customers? What are you doing? How much is it going to cost you to provide that extra level of capacity? One of the beautiful things about cloud is generally there's always going to be enough capacity for anything you want to do. Okay, unless you're really one of the crazy big players like Amazon, in which case basically you have your own cloud system anyway. But even Amazon, what's their busiest day of the year? What? No, one day out of the year typically. Prime Day, if you said Cyber Monday might do it, but I think we'll see. But Prime Day was the one in this last year where they actually experienced network troubles. Even Amazon's cloud capacity fell a little bit short this last Prime Day. So Yeah, Cyber Monday's certainly a valid guess, but this, like I said, the last time we saw like a really big problem was Prime Day. But since Prime Day basically only happens once a year, last I checked, maybe they're doing it twice a year now, it's not worth Amazon's nickel to deal with this problem, right? To put in an extra couple $2 billion to affect a problem that happens for a little while, one day out of the year. Yeah, when they're selling stuff at a discount anyway. So anyway, there's just some thoughts there. So many networks experience significant but transient bursts of heavy traffic, right? And if you have a lot of heavy traffic, we know that's the root of quality of service problems. It's like too many cars on the road, things don't get to where they need to be as fast as you'd like them. So for a network to be robust, and robust is like a network buzzword that kind of means when things go wrong, the network handles it reasonably well. So if you have heavy traffic and your network is robust, that basically in that context it means, well, even though capacity, even though traffic is really heavy, we mostly have enough capacity to manage that, and what we can't, we have a scheme for dropping the least important traffic. So robust networks planned around managing peak demand rather than the average. Because what happens, if you only look at average demand, then when the peak demand spike happens, number one, network performance is going to be crap. Number two, since that's the busiest time, that's when you probably have the most users, you're going to make the most users unhappy in that unit of time. So maybe you don't have enough capacity on hand to deal with every possible future capacity problem, but yeah, you want to come pretty close to dealing with your regularly occurring peak traffic. Anyway, so for quality of service shortfalls, ask questions like, number one, how many users are affected? Number two, what portion of network traffic is affected? And what fraction of the day is affected? Now, these answers tend to be correlated, right? But they also tend to be different. So for example, if you're trying to do one thing behind the scenes in your business, doing some big database cross-checking operation, you're not really affecting many users, right? So that's the sort of thing it's easy to push off to the off hours. On the other hand, if you have a lot of customers who want to shop now, well, you want them to be able to shop now, because if they don't shop now, they might go shop somewhere else. Okay, so depending on what's going on, those are some big things. Now, a historical big case of this, one that was very famous back in the day, Christmas 1999, the Toys R Us crash. And if you search around, right, it's kind of funny now because Toys R Us, right? But back in the day, 1999, Toys R Us was the big toy seller. And Toys R Us, Christmas 1999, holiday problem. See, there it is. You can find some articles about this. And it's listed supply chain management disasters. So there you go. What happened, 1999, the internet was becoming a thing. And so Toys R Us said, hey, we want everybody to shop online. We're going to do a big push. We're going to tell everybody, yeah, don't go to those crowded, crazy stores full of lunatics. Just stay home and have some hot chocolate and shop online. It'll be great. Problem was, they convinced everybody. They convinced so many people that their order fulfillment couldn't even come close to keeping up with demand. So there were a lot of kids, that didn't get their toys that Christmas. Toys R Us had to issue a lot of $100 vouchers to say, yeah, sorry we didn't, fulfill your order on time, but here, come back and buy some extra stuff. Anyway, it went down in the annals as, one of the great problems of history. So basically, this wasn't strictly speaking a network problem. It was a behind-the-scenes order fulfillment problem, but same basic idea. If you can't, service the customers right then, they're going to go somewhere else. Okay. Anyway, moving on. So, video quality, right? Ideally, if you're doing streaming video like YouTube, the video receives every frame in time to be shown, right? So if you're doing like 20 frames per second, every frame should arrive, within like 0.05 seconds, so you get one right after the other, keep showing them as they appear. Okay, but again, for human viewers, different delivery problems get perceived differently. For example, if you have a very high frame rate on your video, 40 frames a second, the human might not even notice if entire frames are occasionally missing. On the other hand, latency and jitter, yeah, those you're going to notice if they exceed the buffering capacity. If the video is always stopping and starting and stopping and starting, people are going to say, yeah, this sucks, right? So in some cases, it might be better, just like an old vinyl record, if there's some hiccup in the groove itself, you just plow right over it like it's not even there and say, yeah, there's a little sound quality issue, but the record keeps playing. It's kind of what YouTube wants to do. Excuse me. Now, interestingly, YouTube doesn't use what's arguably the more technically superior option for delivering content. So here we'll talk about TCP versus UDP. Anybody ever heard of UDP? See, you're learning shit. But you guys have heard of TCP. Some of you. Someone in this room has heard of TCP. I see a couple heads. Oh yeah, I was at this party and we scored some TCP and then my friend passed out on a rooftop in a city he'd never been to. No, not PCP. That's a dog tranquilizer. Don't use it. This is TCP, very different. Okay. Anyway, TCP and UDP are the two big communication problems for protocols, schemes, whatever, for network communication. So TCP stands for Transmission Control Protocol. UDP stands for User Datagram Protocol, and they're both for sending data over networks. So TCP is connection-based. What it does, it finds a path from the source, whatever that data source is, through all the routers that deliver the data till finally the router at your house, right? And tries to send the entire stream of data over that one single path. Okay, so it creates that source destination path, and that inherently allows for data to arrive in the proper sequence, right? Because the first packet that gets pushed into the data stream is followed by the second, followed by the third. And if everything goes right along that path and no packets get dropped, everything gets to the end in the correct sequence. Other thing about TCP, it provides what are called guarantees about packet delivery. Now, in this sense, guarantee doesn't absolutely mean the packet's going to get there. For example, if you send a request to YouTube that you want to download something, blah, 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 so you can watch Pinocchio in HD, and YouTube starts sending it to you, but it's like a gig of data. It's going to take a little while. And while that transmission is going on, your router shits itself and stops working, you are not going to get the last set of packets, right? So it's not absolutely guaranteed that the data gets to you. What this guarantee just means, if there's some temporary short-lived hiccup in the network, the various routers involved in that routing path, they're going to try to resend the packets. So it's basically going to make a good faith effort. If one packet fails to get transmitted from one router to the next, it's going to try again a few times. Eventually, if it goes on long enough and things aren't working, you'll have that kind of timeout error and stuff will stop working. You'll have to resolve that. But it will try at least a few times to keep sending you the stuff. UDP, on the other hand, is connectionless. So connectionless basically means fire and forget. So every packet that the source pushes out toward the destination, it says, well, there you go. Hope you get there. Good luck. Okay. There's no guarantees about delivery. So if some packet doesn't make it from one router to the next along the path, oh well, you just don't get it, right? There's no retransmission. And the other thing, different packets might all be sent on different paths. There's not one single source to destination routing path. So different packets, since they're sent separately, can travel on different paths. So that means the packet receipt order might not match the sending order. It's very likely that some packets will end up out of sequence. Okay? So TCP is connection-based. That's what we mean by a connection. UDP is connectionless. That's what we mean by connectionless. Obviously, there still has to be a path of devices from the source to the destination in both. So in that sense, yeah, there's a connection. But for TCP, we mean a persistent connection. Okay. Bum, bum, bum. So performance comparisons, basically what happens in TCP is something like this. We're going to draw a little picture. So at every stage of the routing process, why is this not working? Shit, I'm having the same problem I used to have. When in doubt, restart. Yeah. Okay, so packets are coming in this way. We have an arrow here. Ta-da, they're going that way, they're going out, whatever. Okay? What's supposed to happen is there's going to be some kind of confirmation. So if I have two devices on the path, A and B, basically what's going to happen, for each packet, or set of packets potentially, that A sends to B, B will respond back to A with a confirmation. Basically, thanks A, I got that. Okay, that's what we mean here by a confirmation. Now, if A doesn't get the confirmation, after, you know, a standard delay, right? Because there's going to allow a few milliseconds for that to happen. A will recognize that the transmission failed and resend the packet or packets. Okay, easy. So every time A sends one or more cluster of packets, at some point B is going to respond back and say, thanks, I got it. If A doesn't get the confirmation, then A is going to think, oh, B never got the stuff. That's how I know I need to send it again. Okay, so there's going to be some delays built in. Number one, the confirmation itself, and as well as any correction, right? So if it tries to send it again, number one, if it has to wait for the timeout for B, that's going to be a delay. And then A has to take the time to send the packets again. There's going to be some delays built in. So inherently, this is what's called, you know, this is a pretty simple, what's called a handshake method. That A sends the stuff and B says, yep, I got it. Okay? If something goes wrong, there's going to be some extra delay. Even if nothing goes wrong, there's going to be a little bit of a delay from that confirmation, right? And if the confirmation is for every packet, the delay can be substantial. Okay. Now, because of that, TCP is going to be a little slower than UDP, right? Receivers acknowledge received packets to prevent retransmission. On the other hand, UDP, remember, UDP is fire and forget. There's no guarantees about retransmission built into the protocol. So, UDP is less reliable than TCP. Any packets that get lost in transmission are going to stay lost. They're not going to come back. Okay? Now, if you're doing true real-time streaming, it makes sense to use UDP. The reason is, users aren't going to rewind the video, right? So imagine if you're sitting in your car, you're driving along, you got the radio on, and you switch stations and you get to hear like the last 10 seconds of some song you really like, okay? What happens? It's just gone. The moment has passed, right? You can't rewind the radio and try to catch up to what was there. That's the idea with UDP. So think about it, for example, if you're playing some real-time video game, right? You're playing something where like you're, I don't know, like Half-Life or Call of Duty or something, and there's a lot of action happening. And whenever it does, you know, you have to react to it immediately. You don't want to have your network clogged up with stuff that happened 1, 3, 5 seconds ago, because that stuff is no longer relevant to the current situation, right? So in that sense, yeah, UDP, if it's true real-time streaming, you don't care about what happened in the past. You just want to have what happens now, and if you miss something, well, so be it. You missed something. Now, the reason why YouTube uses TCP, number one, as we'll talk about in a second, YouTube isn't true real-time streaming anyway. It's basically sequential download of video segments. Number two, some systems may block UDP because basically it's hard to tell if packets are actual responses or part of a denial of service attack. Right? So if you have a firewall, you can draw a picture here. This is a little bit advanced, but we'll cover it anyway. So here is your device, and your computer is sitting safely behind this firewall, and there's some other device out here, okay? So they share information, right? I'm going to label this firewall. Let's make it red. Okay, here's your firewall. Dun, dun, dun. And here's you. And here's YouTube. All right, so with a normal communication like this, I send out a request, right? So say we're doing TCP. I send out a request. The firewall knows the request went out. So when YouTube returns the response, right, basically the video stream, it's expected. Right? The firewall knows, oh, you asked for this stuff. Now YouTube is sending the stuff you asked for. So the firewall lets it through without any trouble. Okay? But with UDP, basically, since every packet is sent out separately, essentially, since packets are sent out individually, and potentially along different paths, it's much harder for the firewall to recognize that they're all part of the same video stream responding to your request, right? It's not impossible that the firewall could set this up, but basically if you're running your firewall with some decent level of security, it's going to look at these things and say, hey, these packets, they're coming from all over the internet. I don't know which one. I mean, yeah, they say they're from YouTube, but anybody can say they're from YouTube. How do you know? Okay? So that's the problem. That's why YouTube fundamentally doesn't use UDP, even though, again, might be technically superior for all the reasons we've talked about. Basically, since firewalls are pretty sensitive about this stuff, YouTube didn't want to let like half the universe say, no, I'm not going to use YouTube because it gets blocked by my security settings. Yeah. Oh, that may be. I mean, they may have aspects of it that are real time, but I suspect even when they do that, it's still, they have it and they deliver it in segments. They don't deliver like every little packet just as it's created. So we'll talk in a second about Dash. I mean, again, I'm not going to say they might not have anything that's real time, but, you know, for 99.9% of the stuff people do on YouTube, certainly it's not true real-time streaming. Okay. Although they might market it as real-time just because it sounds better, even though people aren't, you know, technically proficient to get the difference. Okay, so let's talk about how YouTube actually does it. YouTube, and many other video streaming sites, by the way, use a system called Dynamic Adaptive Streaming over HTTP. HTTP is Hypertext Transfer Protocol, basically the mechanism for delivering data over the internet. So this is called Dash. That's acronym there for Dash. So YouTube, many other organizations use Dash protocol for streaming video. If you're interested, you can like look it up. There's a bunch of them that do. So basic problem is this. You have network conditions that can change suddenly, right? You're watching YouTube in one room of your house, you go to another room, suddenly, you know, there's a big thick wall between you and the wireless device, the wireless adapter, and what? Nothing, right? You get no connection, it stops. So, video player's buffer, yeah, could be overwhelmed, right? Too much data over a temporarily bad connection. For example, if you're walking around your house, around a building, and suddenly, you know, you hit a spot where your connection is terrible, you drop from 5 bars to 1 bar, then all of a sudden, you know, if your video player is trying to download data at the highest possible quality, then suddenly like, might grind to a halt because you can't throw in much data very fast. So the solution is basically to allow dynamic selection of video quality during transmission, preferably at short intervals so the data transfer rate can be closely fitted. Basically, if any connection capacity changes, then YouTube's going to recognize that and say, oh, you got a shit connection right now. I'm going to deliver you video segments in the lowest possible quality. And when the connection gets better, say, oh, your connection is good again. Great. I'm going to give you high quality video segments. Okay. So, remember, high-quality video, whether it's in terms of frames per second or pixel resolution or both, all require more data to be transferred. So, basic process with Dash, you break the video up into segments. Each segment is encoded to multiple degrees of quality. When a new segment is needed, the video player checks its connection speed and its buffer state, and then it selects the highest quality version that it can download without really making the, you know, without overloading the buffer. So, I'll do a little picture here and see what I'm talking about. Okay, so imagine number one. Where are we going to, let's do this in black. Okay. So suppose you have some video segment. Okay, segment. You can have it in high quality, or we'll say highest, high, medium, low, lowest. Okay, and in terms of the data required, maybe the highest quality segment requires this much data, high requires this much, medium, this much, low, this much, lowest, this much. Okay? So then there's you. We're going to make a time graph of what you're doing. So here we'll have time, and we'll have connection quality. Okay? So if I'm walking around, and my connection quality, this is me, at first it's pretty good, and then it dips, and then it dips some more, and then it goes back up. right, what's going to happen? Well, let's shrink this a little bit. Do that about half. Okay. What's going to happen is like, okay, YouTube says, hey, you have a great connection here. Great. I'm going to give you at first this first segment, right? But then I'm going to say, oh, video quality is dropping. Okay. The next segment I'm going to give you is going to be this one. And here, oh, it's even a little lower. Next segment I'm going to give you is like this. And then when I'm really bad, okay, you got some troubles now. Okay, we'll put like one here, one here. At some point, YouTube recognizes, hey, it's getting better again. Okay, I'll send you a higher quality segment. And then when you go back up to the high quality level again, fine, you get the highest one. Okay, does that make sense? That's what Dash is. Okay, pretty simple conceptually. You know, there's a lot of, complicated tech behind the scenes. But basically, it wants to give you the best quality video segment that your current network state can actually successfully process. Okay, just a few more slides. So that's it, right? That's it for the techie stuff. We'll talk open source, closed source, some stuff, and a little bit of other things. So kind of a catch-all here at the end. So number one, Dash is what's called an open source protocol. Open source software generally means that anybody can contribute to the design process. So software development can be public or private. Private is a sense a bunch of guys get together behind closed doors, design the software without the broader public peeking into the design process. When they're done, they release it, and it's the property, it's the copyrighted property of whatever organization developed it. So private is closed source, means the stuff is proprietary. Software is going to be owned by the developer. Good example of that, Microsoft Windows, right? They all design it under Microsoft's roof. When they're done, anytime you buy a machine that has Windows on it, even though you're not paying directly for Windows, yeah, you're paying for it. There's something, there's some kind of, transaction with the computer seller, like Best Buy or whoever, that they paid to put Windows on these machines. Now, because it's closed source, that means you don't have access to the source code. Source code basically means the code that humans can understand, right? So anytime you write up this stuff and programmers are looking at it, that's the source code. When you process it so it actually runs on a machine, that's what's called compiled code. So if you ask why this is open source, closed source means the original source code, how the program is written, that's unavailable to the public. They can't see it. And because of that, because the developer actually owns the source code, it can only be modified as allowed by the developer. For example, your various Microsoft Office applications, you can design plugins for them, right, that do various things. So you can design new modules, you can do add-in features as far as Microsoft allows, but you can't go in there and fundamentally re-engineer Microsoft Excel unless you're part of the team at Microsoft. And how does the business make money? Well, they make money by selling it or licensing it. So, for example, you go to the store, you buy some new video game that's closed source, you pay like $40 for it, that's how they make their money. Or licensed usage, for example, all the ACCC machines around here that have Microsoft Office, UIC says, well, we want 1,000 or 10,000 licenses to use Microsoft Office. They send Microsoft a check for all of that, and Microsoft says, okay, yeah, you can use however many copies simultaneously. Public, on the other hand, is open source. So in that sense, the source code is available, it's just written, it's published, anybody can look at it, and it's not really owned by anyone. The source code has been made public, and the understanding is, it's sort of an open group participation thing to the broader public. So how can you say it's owned by anyone when there's a whole group of people that come in and have contributed to it from outside the organization? So software isn't really owned by anyone, can be developed or modified by anyone, and the revenue, if there is any, you can't sell it because you don't own it. So part of the standard license of open source software development is that you agree that you're not going to try to sell it to anybody. So the way they make money, number one, providing training and tech support. Those are the big ones. So if you guys have heard of Linux, the operating system, that's open source, right? Yeah, it's free. They don't sell it. But what they have for a revenue stream is what? Anybody know? Anybody heard of Red Hat? Red Hat provides this sort of stuff, training and tech support. So if people say, hey, I'm running Linux and I want to put in this new feature, but I don't know how to do it, you can contact with Red Hat and they'll help you actually do the coding for that. Okay. Now, a lot of people in the computer science world are very strong advocates of open source. There's a lot of people too that are kind of like, you know, either one could work. But the people who have strong opinions tend to be very strongly in favor of open source. One of the basic security troubles, if it's closed source software, right, the assumption is nobody gets to look in at the design process, so any security vulnerabilities are tougher to spot, right, from the outside. Unless they're engineered, in fact, by somebody on the inside. But that's a whole nother ball of wax. But the thing is, if a security vulnerability exists in there, it's easier for somebody to miss because they have a smaller number of eyeballs actually involved during the design process. On the other hand, open source, even though the source code is open to anybody, and if there are vulnerabilities in the code, somebody, you know, any bad guy could look at the source code and find them. But the assumption is there are so many more people with varied backgrounds looking at this code during the design process, it's less likely for vulnerabilities to get through. Okay, so again, it is probably generally true that open source tends to have better security than closed source software, but it's not, you know, something with absolute certitude. So, you know, in general, yeah, open source probably does have, I'll give them that. They probably do have better security overall than closed source applications. Okay, but I won't ask you about that on an exam because it's kind of a gray area anyway. It's just a little discussion about, you know, security issues. Okay. So just like Facebook and Google, YouTube needs scalable systems to maintain quality of service, right? YouTube is a huge site. Video streaming is very demanding in terms of network capacity. System has to be scalable. That means it has to work well when it's big. So in particular, there's a big recent increase in mobile usage. So 10 years ago, a lot of people would go to YouTube, watch one video, go away. Now, a lot of people are basically using it as a sort of a Spotify substitute, right? They'll set up their own playlists in YouTube, and they'll have it playing in the background while they're doing something. So yeah, it tends to lead to longer sessions. Also, people are watching a lot of, you know, full-length videos, you know, like movies and stuff on there, not just video clips or songs. Anyway, just like Facebook and Google, system architecture, ideally it wants to handle all requests locally. So just like Google has data centers all around the world to respond faster to local requests, YouTube wants to do the same thing, right? Wherever the videos are stored, it wants them to be stored close to where people actually want to use them. It also tracks trending, right? If videos are getting more or less popular, that may determine whether it's stored at a particular data center and where it's stored within a particular data center. And all this, right, basically predictive analytics to figure out who's watching stuff, how they're watching it, providing backup capacity. Imagine if somebody, I don't know who's popular these days, Taylor Swift, I guess. Imagine if she releases a new video and it's a whole big thing and 1 billion people tune in to watch it at the same time. YouTube's going to need a bunch of different replicas of that on different servers, probably at every data center around the world, right? So they're going to estimate, yeah, a lot of people are going to watch this. Sure, we're going to set that up. Okay, similarities with Facebook. So remember when we talked about Facebook's photo management, Facebooks get uploaded once, hopefully viewed many times, very rarely deleted, right? The only time people mostly throw away videos on Facebook is where after they die and their account gets closed, or if they have a bad breakup with somebody and they want to remove all the pictures that had that person in it. Also, in Facebook, they group photos in albums and they retrieve them in batches for faster delivery, right? All those photos, they're stored on hard disks, and so it's easier, if somebody's going to look at that whole album anyway, it's easier to pull it in one continuous stream from a hard disk than to pick and choose from like 20 different hard disks and incur the seek time delay for each one of those. So the same principles apply to YouTube, right? Videos are uploaded once, hopefully viewed many times, very rarely deleted. And really, a video isn't much more than a giant photo album, right? Essentially a sequence of images, so retrieving a video or a video segment is a lot like retrieving a photo album. But there is one thing, videos are more easily compressed than an equivalent set of unrelated images. The reason is this. Okay, so if you have some scene, for example, suppose first full minute of a feature film is credits on a black background screen. Okay, so what's it all going to look like? It's going to look like, we'll fill that in, and then, I don't know, maybe it'll be in pink for the letters. Written by, I don't know, Susie Sunshine, whatever, okay? And that's the only part of it that's going to change, right? This part that I'm boxing up, everything else for like the full minute, however, like 1,000 frames that might be, everything else is going to be exactly the same background. The only thing that changes is what's in this polygon. So I don't need to send the same frame, the entire frame for all 1,000 times. I say, here's the first frame, and then I say, and then here's what changes in the next 1,000 frames. Okay? So things like that are why videos are pretty easy to compress. Likewise, I could have somebody's in a car, right? Part of the car, like, oh shit, right? Part of the car is I'm seeing this dashboard here, right? And the dashboard fundamentally doesn't change. And there's the sun up here. The sun doesn't change. Most of the blue sky doesn't change, right? The only thing that changes are a few things, right, along here. Everything else basically remains the same. I might not have to, it might be very easy to compress. So reasons like that, videos from one frame to the next, the changes are often small or negligible, and so you don't have to resend the entire frame for every, you resend the entire frame for each next frame in the sequence. Okay. Last thing. So YouTube, last I checked, was a pretty secretive organization. They didn't talk a lot about what goes on in there. So we say, many facets of YouTube's operation are kept secret. We do know a few things. Number one, just like Google, YouTube maintains a hierarchical set of servers to cover its global operations, right? Basically, they have a bunch of different data centers around the world. And if one particular data center doesn't have a video that somebody's looking for, just like Google, if somebody doesn't have an index entry, they can contact another data center and figure out where it is. Videos and other content are, as far as possible, kept locally cached where they're popular. For example, if it's a video in Finnish, well, nobody really speaks Finnish outside of Finland, so chances are, if there's a Finnish language video, unless it's become a surprise worldwide viral sensation, chances are it's just going to be stored on that one data center wherever it is by Finland. Okay? And again, for the same fundamental reasons as Facebook. You want to keep data close to where people want it the most. Anyway, these details, there were a few research papers, like around 2011. They looked into this. Basically, they re-engineered YouTube's video stream. So they did a bunch of oddball video requests, so things that should be local. So there were things that were locally popular and other things that they figured would only be popular in other parts of the world. And they picked apart all the packets, looked at all the packet headers to see what the source IP address was from where things came. And yeah, they verified that basically, you know, in case there was any question, all this first stuff, that's obviously the sensible way to design this system. But these guys actually went ahead and proved it by looking at the information in the video packet data. Okay. Questions on any of this? You got stuff? All right. Well, if you do have questions, right, you know we'll have a review session eventually.